And we'll start with the current slide. And I'll turn on the projector. Okay, forgot to do that. A couple of announcements. I've seen posted on the walls the Taming of the Shrew, I think is a UAB theater production, is going to be on the Birmingham East Campus this Friday, 10 o'clock, I believe it is. Check the flyers that you see posted on some of the doors and walls around the campus. It's a Shakespearean play, a comedy. The original was, and this one is supposed to be as well. Basically, Shakespeare's story was the woman was very, very difficult to handle, and the man was trying to tame her, and it brought for a lot of laughs and funny situations. From what I read, the UAB production has decided to twist things around, have the man very difficult to deal with, and the woman trying to tame him. I think, what's new? I mean, I didn't say that. No, okay. But anyway, it still should be a good production. And that's this Friday, Birmingham East Campus, the A.G. Gaston Building, at 10 o'clock in the morning on Friday. That's my understanding. Check the flyers and make sure that's correct. Okay, the other thing, and this one is specifically for this class, and that's why one reason I'm so disappointed there aren't more people here. Last year, first year we ever had a math team, okay? So we sort of got a late start because we just formed a team, but we did fairly well, okay? At the only competition we went to, okay? And this year, we started just as late as we did last year, and I don't think we did quite as well. And the coach, Mr. Racy, really wants to get started much earlier. In other words, start planning for math next fall now, okay? So I'm hoping you're still going to be around next fall, aren't you? Not? Okay. Well, for the rest of you, Brittany's the only one in the room right now. For the rest of you, I hope that some of you will be here next fall, still taking math, which means maybe calculus and that kind of stuff. You are exactly the people we need to be thinking about joining the math team. So if you can, please contact Ms. Geraci. Her email address is jaraysi @lawsonstate.edu. That's Geraci, JARAYSI @lawsonstate.edu. Please contact her. She's wanting to set up an hour-run practice sessions out here. If it's more convenient, she said she could come out here certain days. I think she's wanting to hold them on Fridays. Well, I'm on the Birmingham campus on Fridays, but anytime during my office hours, Monday, Wednesday afternoon, 3:15 to 5:15, or Tuesday, Thursday afternoon, 1:15 to 3:15, we can hold them. And then on Friday, I can do them on the Birmingham campus since I'll be there, but she'll be out here doing them. So, but she'll set every other Friday here and every other Friday there. So anyway, please consider it. It's a lot of fun, and actually, you learn a lot of math from a fun perspective, and that's going to help you in your upper level math courses. Big time, okay? You'll be familiar with that stuff, with the rest of the class is clueless. So it's a good advantage to you to consider the math thing. Hopefully some of you will come in and I'll tell you in person. Okay. So any questions or anything we've covered so far? We're in Chapter 5 now, which is analytic trigonometry, and 5.1 is using fundamental identities. We did example 1, here's example 2. Simplifying a trigonometric expression. There's an expression. We want to simplify it. What would be one step to simplify that expression? Since we don't do it as much in this class as I do in Math 100 or 112, I may not have told you my little, we've just tripled the class size, okay? Whitney's here. And Chastity's here. Okay. I said this earlier, but you may not go back and listen to it. Are both of y'all going to still be here next fall? No?
Next fall.
Huh?
Spring.
You graduate in spring?
Uh-huh.
Oh, man. Both of you?
Yeah.
Oh, shucks. Okay. Elsa, surely you'll be here next fall, won't you? Yeah? No? Oh, man. Yeah, one year from now.
I won't graduate.
Oh, really? Okay, I was hoping y'all would be taking calculus next year.
Oh.
But you won't come back and do here, you don't think, when you graduate? What's that?
I said no, I'm going to be out of Alabama.
Oh, I see. Okay. Sorry about that. I was hoping to have all of you for calculus, but sorry.
I'm taking calculus in the spring though.
In the spring,
Mm-hmm.
Fantastic. Okay. But what we're asking for is math team, and they, yeah, yes. I do, but usually in the summertime. Usually we don't have enough students to make 2 sections of physics. Well, we have 2 levels of physics: trig-based physics and calculus-based physics. Now, we don't, and then there's 2 levels there. There's mechanics, and then there's electricity and magnetism. So there's 2 classes in each of those. Most of the time, we don't have enough students to make a class of each. So we stack those 2 classes because mechanics is still mechanics. It's just what level of math you use to teach it and to solve it. Same thing with electricity and magnetism. The principles of physics are the same, it's just the level of math. So what we usually do is stack those together and have 201 at the same time as 213 and 202 at the same time as 214. If we have enough to split, then I teach one and Dr. Bryant teaches one. But if we don't have enough to split, he teaches the stack class. I have taught it before, but since he is more credentialed to teach it than I am, his credentialing is better, and that's what he likes to teach. His PhD is in physics, then I let him teach that. So most of the time, fall and spring, he teaches the stack classes. Now, once we get enough students to split them, then I'll be teaching it too. In the summer, however, when we have lots of transient students come in from other schools that home for the summer and wanting to knock some of the physics out, then we usually have enough to make 2, and I usually teach it in the summertime. Okay, but not usually fall and spring. So I put it on the schedule, hoping we'll have enough students, but just like always, we wind up having to stack them, and he winds up teaching. So you'll see my name on it, but the odds are I won't be teaching. All right. Doc, surely you'll be here next fall, won't you?
Who, me?
Yes.
Okay.
You will?
I will.
You will not. Oh, man. Striking out on all accounts. I'm trying to recruit for next year's math team.
Oh, yeah.
And, oh, yeah. Okay. All right. Okay, let me mark you here, though, even though you won't be here next year. Okay. And I got Elsa when she came. Okay. So, Elsa, are you dual enrolled? Is that what your status is? Okay. Do you know if I need to report anything for you midterm or anything else? I haven't heard of anything. Okay. All right. I know at the end of the term I have to put letter grade and number grade if that works still the way it did. All right. Chelsea, right? Okay.
I think I'm just supposed to get my stuff like a regular student.
What's that?
I said I think I'm just supposed to get like my grades and stuff like a regular student.
Okay. Are you on a formal program or are you just sort of doing it yourself?
No, I'm not. I'm with like the enrollment grade.
Yeah, okay. Yeah. Well, then I think I have to report your grades 2 different ways, letter grade and number grade. I don't know why, but I do. I guess it's for calculating things in high school. Chelsea, are you going to be still here next fall? Or are you graduating before then?
I mean, I'm just a transient.
What's that?
I'm just a transient.
Oh, you're a transient student also. Okay. All right. Sorry, we're recruiting for math team for next year, and we need to have people who will be here in the fall. Okay, good deal. All right. Any questions before we get started? We were trying to simplify this trigonometric expression. And Brittany was so happy the rest of y'all came in because it was just she and I. And so she was going to have to answer all the questions, so she's happy she's got some help. How would you go about simplifying that expression? Okay, sine squared. You're right. And we are going to use that a little later, but one step to do before you get that far. Okay? Now, say again? Okay, not divide by, because this isn't an equation, it's an expression, but factor it. Okay, now, I was just saying before y'all started coming in that in my other classes, now I don't want to say this if it offends anybody, but in my Math 100 and 112 class, the algebra classes, we do a lot of, to simplify, the first thing you look at is factoring. So when I say, what's the F word, it's going to be factoring, right? So I don't want y'all to get it. If that offends any of you, I won't use it, but, if it's okay. So that's what I suggest we do here, factor. What can we factor? Can we factor anything? What you were suggesting? Factor out the sine x. Okay? Sine x is not 6, okay? Okay, sine x. Okay? And what does that leave us with? Cosine squared x. There's more. Minus 1. Exactly. Right? Does everybody see that? Now, what's the next step? And this goes to something Ilsa was just mentioning. What did you tell me? Okay, she just said that cosine squared x was equal to 1 minus sine squared x. Okay? Now she said change it to that, and you can. Let's go on and do it that way then. This will be sine x, that's a factor, don't throw it away. And instead of cosine squared x, we're going to put 1 minus sine squared x, right? That's cosine squared x, minus 1, right? Well, what does that give us? 1 minus 1 is 0, okay? So that gives us sine x times a negative sine squared x, and that gives us negative sine cubed x. Very good. We have just simplified that mean and ugly looking thing to something that's much simpler. Right? All right. Does that make sense? That's the type of thing we're going to be doing for this whole chapter almost. Not quite, but a good portion of it. At least this section and probably into the next one. Okay? If you're any questions on that? Let's see how they did it. Oh, still writing? Okay. All right. So let's see how they do it. They say, first factor, okay? The common monomial factor, and then use the term fundamental identity. So we first factor out the sine. Common factors here, sine x, that leaves us cosine squared x minus 1. And now, here's what they did. It was similar to what you did, only you plugged in. What they did was, look, here we have cosine squared x minus 1. I know that 1 minus cosine squared x is sine squared x, but this is the reverse of that. So let's factor out a minus 1 and change both of these signs. So they factored out a minus 1 and left a sine x times 1 minus cosine squared x. 1 minus cosine squared x is sine squared x. So it's minus sine times sine squared x, which will be, just like we got, minus sine cubed x. Same way, same procedure. We used a different procedure, but every step was right, and we came up with the same answer, which surely you should get. As long as you're doing correct steps, even if you take a different route, you should wind up with the same answer. That is the simplified form. Does that make sense? Now, we don't divide here because you only divide things when you have equations. When you have expressions, you just simplify. Okay. Whoa! They jumped from example 2. And by the way, every example is followed by a checkpoint. As soon as you can, go back and do your checkpoints. So let's jump back and do example 3. Factor each of the following expressions. So this time they're just telling you, they don't say simplify, they just say factor. Okay? So here's a secant squared theta minus 1. Now they said factor it. Frankly, I wouldn't factor it, but that's what they're telling you to do. How can you factor that? That's a difference of two perfect squares. How do you factor that? Secant theta plus 1 times secant theta minus 1. Now, they told you to factor it, we factored it, okay? And that's all they wanted you to do. Now, here's why I said I wouldn't have done that, okay? If it said simplify, here's what I would have done. Does that look anything like a trigonometric identity? Secant squared theta minus 1? Which one does it look like? It's one of the Pythagoreans. Anyone that has a square in it usually is a Pythagorean. That would be exactly, anyone know? That is tangent squared theta. So that's what I would have done. I would have just changed it to tangent squared theta. But they said factor it, so we factored it. Fine, good, so what? Okay. Let's do the B part. It says factor this. 4 tangent squared theta plus tangent theta, minus 3. Now, how would you factor something like that? I've already given you a hint. It's a trinomial, right? It's not that your variable is x now, it's tangent theta now, okay? But you treat it just like the same way, okay? And you would do, okay? You're going to factor the first as tangent theta times 4 tangent theta. Is that what you're going to say? Okay. So let's do a tangent theta times a 4 tangent theta. I think of it as unfoiling it, you know. And what about our signs here? S-I-G-N signs. What does this indicate? These two have to be 1 plus and 1 minus. Absolutely. That's the only way you're going to get a minus there. Now, the thing that is multiplied, okay, so let's do it. So one of these is plus and one's minus. You can get to choose. What's the only factorization for 3? 1 and 3. So you tell me what to write down. Plus 1 and minus 3. Okay, let's see if that works. Tangent times tangent, I'm going to pull it and see. Tangent times 4 tangent would be 4 tangent squared, right? This will be minus 3 tangent theta plus 4 tangent theta would be plus tangent theta minus 3 plus 4 is plus 1, and then minus 3. That factors exactly.
Wait, isn't it?
What's that? For you.
Wouldn't it be 2 tangent theta?
You mean have it 2 and 2?
No, I'm saying isn't this wrong? Like, aren't the signs wrong? Because wouldn't it be 2 tangent theta?
Okay. Let me get. Hey, look, you're right. Yeah. All right. You mean the way we got it? Huh? You got it. Okay. All right. Good deal. So we factored it. Okay. Now that one, I can't see any better way to do it than to factor it. And when you're solving equations, like if either one of those, if this thing here would have been equal to 0, or this thing here equal to 0, yeah, you're going to factor it and then solve each of these separately. Secant theta equal minus 1 and secant theta equal plus 1. Yeah, if you had an equation there with that, tangent theta, square theta, probably it's going to help you as much as factoring it and then solving each one individually. Okay? So, let's move on to example 4. Any questions about 3 before I delete it? What we're doing is factoring trigonometric expressions. You just treat the trig expression as if it was a variable and factor from there. Okay? So let me delete or erase all the ink, virtual ink anyway, off the slide. Ionic ink. Okay? Factor this one. Cosecant squared theta, one of my favorites. Is it theta or x? No, this is x this time. Okay? Minus cotangent x minus 3. It says factor that. Houston, do we have a problem? That would be sort of like saying factor this. A squared minus b plus minus 3. How can you factor things with 2 different values in them? One. Yeah. Okay. See the problem? Now, probably the best way to deal with this, anytime you see a square and you can't think of anything else to do, think about your Pythagorean identities. Is a Pythagorean identity that somehow relates cosecants with cotangents? And please say yes. Oh, okay, what is it? That was the trick, okay. What's that? No, secants and tangents go together, and cosecants and cotangents go together. Okay? If you flip back just that one page, okay, one sheet of paper, okay, until you see on page 350, your Pythagorean identities are right there, and notice the third one listed is 1 plus cotangent squared is equal to cosecant squared, right? Very similar to the one for tangents and secants, right? So instead of cosecant squared, we're going to write 1 plus cotangent squared x, right? Minus cotangent x minus 3. Okay? What would you do with that? Now Houston has gotten a lot better. We don't have 2 different variables there. You got the same variables, thinking of the trig functions as if they were variables. But what do we need to do first? Yeah, combine like terms. 1 minus 3 is what? Second? Negative 2. So we have cotangent squared x minus cotangent x minus 2. Okay? Now what would you do? It told you, factor it. Okay? This you can factor. You can't factor if you got cosecants and cotangents both in there. You can factor if everything's in cotangent. So what would be the only possible factorization of cotangent squared? Cotangent times cotangent. Okay? You look at the last term, first at the sign. What does it tell you? One's going to be a plus, one's going to be a minus. And then we look at the 2 and say, what's the only factorization for 2? 1 and 2. Now, I also want to ask myself, who wins? Who has to be the bigger value? The minus sign. So put the 2 here and 1 there, and we should have it. 1 here, 2 there. I always like to check because I don't like to make mistakes. So cotangent times cotangent is cotangent squared. That works. Minus 2 cotangent plus cotangent would be a minus cotangent, and that gives us a minus 2. Yes, we got it. Okay? So we have now factored that messy looking thing that had both cosecants and cotangents in it. Now, any questions on that? Everybody see it? All right. Let's now go to example 5. Simplifying a trigonometric expression, which is what we've been doing. And let's take a look at one that's a little more messed up, okay? Here's a sine t plus a cotangent t times a cosine t, okay? How are we going to simplify that expression? What we did before, factor out common factors. Do you see anything in common here? There's nothing in common there, okay? So what are we going to have to do? In fact, every trig function is different. Those are hard to simplify. So here is a clue. If you can't see anything obvious to do, here's my little rule. Get everything you can in terms of sines and cosines. Simplify that way. Sine is already in terms of sines, so yes.
So we're not working in the other side?
Okay. Actually, in the book, if that's where you're looking, on the right-hand side is just the first step in simplifying the left-hand side. They should have written that underneath. Okay. They have something else there, but that is just the first step in simplifying. Okay. In a while, we're going to be talking about identities, and that's, I think, what you're thinking. This is not one yet. We're just simplifying. And here is Justin. Okay, I've forgotten the last couple of people who came in. 3 people, in fact. Are any of you folks still going to be here next fall? Yay or nay? Yes or no? 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 Yes. Okay. 5. If there's a chance you still may be here next fall, we would like you to seriously consider being on the math team. Now, we're not going to have any competitions before next fall. That's why I was asking. But the time to get ready for next fall's competition is not next fall, okay? You need to start getting ready now. So, Mr. Racy, who's the coach of the math team, is trying to get names for all the people who may be interested. So, if you are, could you email Mr. Racy? It's njaracy, JARAYSI, at lawsonstate.edu, and tell her you're interested in participating. Now, I will help run practice sessions here on this campus. She's mostly on the Birmingham campus. But she said she was thinking of having practices every Friday, and she would alternate which campus she would be on. Well, I'm on the Birmingham campus on Friday, so I can do it there, but I can't do it here on Fridays. But I can do it here either Monday, Wednesday afternoon, 1:15 to 3:15, or any time in there. I'm sorry, Monday, Wednesday afternoon, 3:15 to 5:15, or any time in that time slot. Or Tuesday, Thursday, any time between 1:15 and 3:15. Not today, but most days. Okay, so if you are going to be here, any chance you'll be here next fall, please consider that. You are our best prospects for math team people. You're in trig already. Hopefully you're going on to calculus. Okay. Now, what I was suggesting was, anytime you can't see anything else to do, nothing reaches out and grabs you then, get everything in terms of sines and cosines. Sine is already in terms of sine, so just write it down. How about cotangent? What is that in terms of sines and cosines? That's cosine t over sine t, right? And then multiply that by cosine t. So just bring that one down. All right. Now, what you can also do is just write that under that, because that's all numerator stuff, so you can multiply it together. What we have now is a fractional form. This is in fractional form, this one's not. You're trying to add things that are fractional. What do you have to have if you're going to add fractional entities? Same denominator. So you need to have a sine t over here. So to get a sine t over here, we'd have to multiply the denominator, which was 1, by sine t, but you would also have to multiply the numerator by sine t. Because what is sine t over sine t? 1. And when can you multiply by 1? Anytime you want to. It doesn't change the value any. Okay? Well, what's cosine t times cosine t? That's cosine squared t. Okay, so you have sine squared t plus cosine squared t all over sine t. Because anytime you're adding two fractional forms with the same denominator, add the numerators to keep the denominator, right? If that was 1/3 plus 2/3, it would be 1 plus 2 over 3. 3 over 3. Okay. Now, what is sine squared plus cosine squared? 1. So this is 1 over sine t. And what's 1 over sine t? Cosecant t. There we simplified it, just about as simple as you can get. You went from 3 different trig functions, added and multiplied, to one single trig function by itself. I would say that's simple. It's in cosecants, which are not my favorites, but it is as simple as you can get it. I'll try to even clean up my writing a little bit so it's easier to read. Okay. That was example 5. I think they also aren't going to do example 6, so let's do example 6. Any questions on this one before I erase it? Okay. Everybody got it? Okay. Example 6, last one we do before they start doing them again. Perform the addition and simplify. Here we have a sine theta over a 1 plus cosine theta, right? We're going to add to that a cosine theta over a sine theta. Okay? We want to add those things and then simplify our answer. Same question I had before. What's the first thing you got to do? You're adding fractional forms. So what do you got to do? Yeah, you got to get the same denominator. Okay? Common denominator. And since these have no factors in common, it's going to be the product of the two. So you're going to have to multiply the first one here by sine theta, right? Yay or nay? Okay. Yay. Okay. Sine theta. But if you multiply the denominator by sine theta, you got to multiply the numerator by sine theta as well, right? You got to multiply the second one by 1 plus cosine theta. But if you multiply the denominator by that, you also have to multiply the numerator by 1 plus cosine theta. Okay? Now, you've got common denominators. I'm not going to multiply them out. I left off the theta here, didn't I? Okay, cosine theta. My nose is itching. We must be going to have company. Okay. You never heard that?
No.
Really? My mom used it all the time. Okay. Okay. So we got our common denominator, so I'm going to write it down. Sine theta times 1 plus cosine theta. There's no reason to multiply them out unless there's some advantage I don't see any to do. But what's our numerator? Sine squared theta for the first one plus cosine theta plus cosine squared theta. Okay? Now, anything looks like it might be useful to do. Okay? Yes, you could, but how about let's just combine sine squared theta plus cosine squared theta. What is that? 1. So just add those two. I mean, identify those two as 1. So you got 1 plus cosine theta, right? That's all you got in the numerator, right? Because these two add to be 1. And in the denominator, you have a sine theta times a 1 plus cosine theta. And guess what? 1 plus cosine theta over 1 plus cosine theta is 1. So what do we have? 1 over sine theta. They seem to like that, don't they? Because what's that? Cosecant theta. Exactly. The last one was a cosecant theta. Now, believe it or not, what we'll wind up doing either later in this section or the next section would be take something like the left-hand side of example 5, setting it equal to the right-hand side, well, the right-hand side to be what we had to begin with here, and say, is that an identity or not? And what we would do is break them both down all the way and say, yeah, it is, because they're both equal to the cosecant theta. We're not doing that yet, but we will. There is a checkpoint. Like I said, every one of these has a checkpoint, so please take advantage of those as soon as you can after class. All right, any questions? Let's see if we can find, example 7 now. Goodness gracious. Y'all don't probably care about this even, but yesterday on my way to work, everything was running nicely except one light had come on, but it was traction control light. And I wasn't on slick roads. I wasn't pressing the brake. It just popped on while I was on the getting on the expressway. Wow. Everything seemed okay. Car was running fine, so it came on. Traveled about, 15 miles on the interstate. Everything seemed to be fine. When I pulled off the exit to come to campus here, Splash Adventure Parkway back there, and stopped at the stoplight, my car shut down. It was really hard to get started again. So what is going on here? Has nothing to do with traction control. But I got it started. I limped onto campus and barely made it up the hill. It tried to shut down on me again. I parked it. And then yesterday afternoon, after my classes were over, I started calling around to see what I could do. And it wound up that the guy advised me not to drive it, to have it towed. So I tried to call the towing place that they used and they couldn't get out there last night. So this morning I had to take Uber into work. The rental car place my insurance company uses didn't open until 7:30. And then when they did open, they said they wouldn't have a vehicle till this afternoon. So I had to take Uber here to campus. So I was late getting here. So it's been a crazy day. So if I'm kind of wacko, that's part of it. All week so far has been a little crazy. All right, let's do example 7. Rewrite this, 1 over 1 plus sine theta, so that it's not in fractional form. So what in the world would we do to make that happen? How do you rewrite that so it's not in a fractional form? Any ideas? Okay. Now, if the problem would have been something like 1 over 1 plus the square root of 2, and I said simplify that, what would you do next? Do you remember the little technique or rule? The what? It's called the conjugate. Great idea. Is that what you're thinking? Not the denominator, by the opposite sign in the denominator. It's called the conjugate. That would be my first attempt here. Okay? Multiply the denominator by 1 minus sine theta, and multiply the numerator by 1 minus sine theta. Now that may not work, but that is going to be kind of a fallback for this kind of problem. If you can't think of anything else, multiply by a conjugate. Now, why the conjugate? Okay? Well, let's do it and see. The numerator just becomes 1 minus sine theta. So that made the numerator more complicated. So maybe we're going in the wrong direction. But what does your denominator become now? Tell me it's that hard. 1 minus, say again, sine squared theta. Is that what you said? Do you see that? Yeah. I mean, pull it. 1 times 1 is 1 minus sine theta plus sine theta. Middle terms go away. Minus sine squared theta. Yeah. 1 minus sine squared theta. Now, what's an advantage of that? What is 1 minus sine squared theta? That's cosine theta. So this will then be 1 minus sine theta over cosine squared theta. Okay? Now, here is an advantage. When you have a sum or a difference in the denominator, there's not a lot you can do. But if you get a monomial in the denominator, not a binomial, but a monomial, then you can break this into 2 pieces, right? That would be the same as 1 over cosine squared theta minus sine theta over cosine squared theta, right? If you have the same denominator and you're adding or subtracting things, keep the denominator, add or subtract the numerators. Well, this is just doing the reverse of this. If you have an add or subtraction in the numerator and a common denominator, split it and make it each. Well, what is 1 over cosine squared theta? Without being in a fractional form. What's 1 over cosine? Secant. So 1 over cosine squared would be secant squared theta. I can't write. Okay? Minus, now, sine theta over cosine theta times 1 over cosine theta. Isn't that sine theta over cosine squared? Here we're factoring this, sine theta times 1, cosine theta times cosine theta. What is sine over cosine without using a denominator? Tangent. So now we have secant squared theta minus tangent theta. How about 1 over cosine? What's that? Secant theta. All right. Now, there's a little bit of me that says, hey, you got a common denominator secant theta here. So factor that out, and you'd have secant theta times secant theta minus tangent theta. Yeah, but what can we do with that? Nothing. So this form is just as good as doing that next step. This is perfectly fine. Notice what we did? We rewrote that so it's not in fractional form. Is it any simpler? Well, not really, except it doesn't have any denominator. So if you don't like denominators, you might like this better. If you like fractions better than you like things like this, then leave it in that form. But no, they told you to write it so it's not in fractional form. Does everybody see it? Okay, let's see what. Yep. Let me erase this if there's no questions. Let's see how they proceed. All right. Here's what they did. They said, because from the Pythagorean identity, cosine squared, there's no cosine squared there, is equal to 1 minus sine squared, but there's no 1 minus sine squared there. So where did they get that? Well, they knew where they were heading, so they told you how they got there. But without knowing how you're heading, the trick is try multiplying by the conjugate. If you can't think of anything else to do, you already got it in sines and cosines, you can't think of anything else, you got a denominator, which is a binomial, multiply by its conjugate. So that's what they wound up doing, but they say because, but you see, you didn't know that, I mean, that's what you're looking for, but just try it, multiply by the conjugate. Let the numerator and the denominator by 1 minus sine squared, which is what we did, and that then will produce 1 minus sine squared over 1 minus sine squared. 1 minus sine x over 1 minus sine squared x. Okay? And then we know this is cosine squared. So that's why it was advantageous to multiply by the conjugate. Okay, so that's 1 minus sine x over cosine squared. Split that into two fractions. Write a separate fraction, 1 over cosine squared x minus sine over cosine squared x. Perfectly legal in most states. And that would be, now split the second term into sine x over cosine x times 1 over cosine x. Again, legal move. And 1 over cosine squared is secant squared. Sine over cosine is tangent. And 1 over cosine is secant. So now we have secant squared x minus tangent x, secant x, no fractions, done. Make sense? Could take it another step by factoring out a secant, but it doesn't improve it any. It's just another form. Whoa! That was the last slide they show in the PowerPoint. However, there's two more examples, so let's back up and do example 8. Now this time, they give you what they call a trig substitution. Well, I call it that because for those of you who do proceed to calculus and calculus 2, you will be doing this very kind of substitution. But here's the substitution they tell you. X equal 2 tangent theta. That kind of substitution. Now, here we're going to limit our theta to be between 0 and pi halves. Okay? Now, it's not probably obvious why you would do that. Okay? let me write the rest of the problem down. That may not make it that much more obvious, but it will suggest something. You're going to use this substitution to write this expression, the square root of 4 plus x squared, okay, as a trigonometric function of theta. Okay. Now here's why you do this. The pi halves is easy. We know that tangent of pi halves is not even defined, right? Because that would be sine of pi halves over cosine of pi halves. Sine of pi halves is 1. The cosine of pi halves is 0. And you can never divide by 0. So that's why you have to keep the theta less than pi halves, because it's not even defined at pi halves. Okay. Now, it is defined anywhere from negative pi halves to pi halves, but they didn't include negative pi halves. And here's part of the reason for that. We want to make sure that x is not absolutely required, but it's usually better for it to stay positive. And you see, for theta less than 0, between pi halves and 0, that would make your tangent negative there. And even though you're squaring this thing, and it would not be an issue for this to remain to be a function, we want it to be positive. Now, again, it's not absolutely necessary, but they chose to do that. All right, well, let's do what they told us to. You do the square root of 4 plus, but instead of x, you write 2 tangent theta. So that would be 2 tangent theta squared, right? All right. That would be the square root of 4 plus, now what's 2 tangent theta squared? 4 tangent squared theta, right? Now what can we do with that? Factor out, good deal, factor. Factor out of 4. So it'll be the square root of 4 times the square root of, what's left? 1 plus tangent squared theta, right? What's the square root of 4? Second, 2. Now, what is 1 plus tangent squared theta? Secant squared theta. And what's the square root of secant squared theta? Secant theta. You got it. Now, here's the other part of it. A lot of times when you're taking the square root of a perfect square, you put plus or minus here. But if we restrict ourselves to only first quadrant, 0 to pi halves, everything's positive there. So you don't have plus or minus here. So that's finally the other reason they didn't include the minus. If you stay in the first quadrant, you can take the square root of secant squared and just call it secant. Because square roots are principal square root is always positive. Okay. And that's what they got. Okay. Sorry. My throat feels like it's going on me. All right. There is a checkpoint, like I always say, look at the checkpoint. Take a look at them. Now, here's something else. They draw this little figure here for you. And let's imagine this is a right angle. So that makes it a right triangle. And let's just imagine this is our angle theta. Okay? Now, if you're using this trig substitution, okay, what we have here, you could divide both sides by 2 and have tangent theta is x over 2. Well, what is tangent theta? Back to our original, taking oats away. Okay, but let's go back to taking oats away. It is tangent is opposite over adjacent, right? Way back to the very beginning. Opposite over adjacent. Well, if tan theta is x over 2, you can say this is your opposite, x, and this is your adjacent, 2. Okay? Now, guess what? From Pythagorean theorem, what is your hypotenuse then? What is your hypotenuse? X squared plus 4. Square root of x squared plus 4. Which is exactly what we started with. Only they wrote it 4 plus x squared. It's exactly what we started with. Is that. And we sure enough saw that that expression is, think about this. Secant theta is hypotenuse over adjacent. So 2 times secant theta is this. So yeah, that's one of the things I love about trig. Everything ties together and it makes such perfect sense. You know where to look. All right. Now, any questions on that before we go? So let's do example 9. Let's rewrite this expression. The log, natural log, of absolute value cosecant theta plus the natural log of absolute value tangent theta. Okay? As a single logarithm and simplify the result. Whoa, this is more than trig here, folks. It's got some logs and exponents, that type of thing in it. So, does anyone remember some of the rules for logarithms? The log of a product is the sum of the logs. Do you remember that? Okay. I think it's the back of your book. There's algebra. There's trig. On the very back of your book, that last page is sort of heavier duty material. Tell me it's not here. Yeah. No, this is. I'm sorry. It's on the very back cover. Algebra. Okay. Exponents and radicals. No, it's not there either. Maybe it's not in your book. I was thinking it was. All right. So what you have to do is go to chapter 6. No, 7. Chapter 7. No, sorry. Chapter 4. No, 3. Chapter 3, finally. Chapter 3. If you go to the very end of the chapter there, well, no, it's not there either. Yes, it is. If you go to page 251, it's called the power property. No, it's number 3 there. Section 3.3, number 1, the product property. The log, whether it's natural log or base A, but let's look at natural log. Log of a product, log of u times v, is the log of u plus the log of v. Right? See it there? It's called the product property of logarithm. Well, let's do that in the reverse. Now we have the sum of two logs. That means it's the log of the product of those two. So that, from our log rule, that would be log of cosecant, not cosine, cosecant theta times tangent theta. That would be what that sum of two logs are, the product of their logs. The log of the product is the sum of the logs. Okay? Now, that actually is the first thing it said. Write it as a single logarithm. Done. Simplify the result. How do we simplify that? Say again? Get everything in terms of sines and cosine. Excellent choice. So that would be the log of, and what is cosecant in terms of sine and cosine? 1 over sine theta. And what's tangent in terms of sines and cosines? Sine theta over cosine theta. Right? Sine theta is divided away, and that gives you the log of 1 over cosine theta. What in the world is 1 over cosine theta? So this is the log of absolute value secant theta. Now, if you knew that theta was always in the first quadrant, you can lose the absolute value sign. But there's nothing in the problem that says it is necessarily, so I would keep it in. Any questions? Well, that finishes 5.1. Let's look at the vocabulary for 5.1. 6, fill in the blanks. Fill in the blank to complete the trigonometric identity. Number 1, sine u over cosine u is what? Tangent u. Number 2, 1 over cosecant u is what? 1 over cosecant. Sine, exactly. Number 3, 1 over tangent u is what? Cotangent u. Number 4, secant of pi halves minus u is equal to another name for pi halves minus u would be the complement of u. That would be cosecant u. You're absolutely right. Number 5, 1 plus blank is cosecant squared u. Is what? 1 plus blank is cosecant squared u. A Pythagorean identity. What? Cotangent squared u. Exactly. And number 6, cotangent of negative u is equal to what? Looking for even or odd functions is negative cotangent u, because cotangent is an odd function, so that would be negative cotangent u. Very good. Homework exercises. Any of the odds 7 through 13, any of the odds 15 through 19, any of the odds 21 to 27, either 29 or 31 or both. Do 33, only one like that. Do any of the odds 35 to 43. Do either, 45 or 47 or both. Do 49. Do 51. Either 53 or 55 or both. That's very similar to what we just did in an example. Do 57. Do 59. Do either 61 or 63 or both. Do 65. Okay, the exploration There's one odd, true, false, well worth looking at. Don't expect them on the test, but well worth looking at. Finding limits of trigonometric functions. Use it. I think you could do that one. And then determining identity, 71. If you want to try that, you can. And then 73 and or 75. You can look at those if you want. All right. Any questions on 5.1? Okay. Let's move on to 5.2. Thing is taking a while opening. Here we go. So let's go from the current slide. Okay, again in 5.2 we're still in analytic trigonometry. This time we're going to verify trigonometric identities. Now before we launch into this, we sort of have to, the objective is to verify trigonometric identities, which is the title of the whole section. Okay? But the introduction here is going to talk about what an equal sign means, right? Most of the time an equal sign will exist in an equation, and that's still the case, of course. But there's two types of equations. In this section, you'll study techniques for verifying trigonometric identities. Most of the time when we see an equal sign, we think of that as a conditional equation. It's an equation that is true only for some of the values in the domain. For example, if we say sine x equals 0, is sine x always 0? No, only for certain values of x. Name some. When is sine equal to 0? At 0, pi, 2 pi, 3 pi, 4 pi, negative pi, negative 2 pi, all of your pi's, all your whole pi's. If x is a whole pi, sine x equals 0. If x is not a whole pi, I like the idea of whole pi, but then the sine x is not equal to 0. That's a conditional equation. You find the values of x and make that true. And we say that's true for only n pi, where n is any integer, positive or negative. Okay? But sometimes equal signs show up in equations that are not conditional equations. Okay? On the other hand, an equation that is true for all real values in the domain of the variable is an identity. For instance, sine squared x plus cosine squared x is always, always, always equal to 1. That's an identity. That's not an equation, a conditional equation. That's true for every value x you put in there. As would be when you subtract the cosine squared from both sides, sine squared x is equal to 1 minus cosine squared x. Always true. Okay? For every real number x. So that's called an identity. So what we're going to be doing in this section, they're going to give us expressions with an equal sign in between, and you determine whether they're identities or not. Are they always true for all values? If they are, they're an identity. And they will say, verify that's an identity. And that's what we'll be doing, verifying the identities. Although there are similarities, verifying a trigonometric equation as an identity is quite different from solving the equation. Because what are some of the things you do when you're solving an equation? You do the same thing to both sides. Like you add the same thing to both sides. You multiply the same thing to both sides. You divide the same thing. You subtract the same thing. You take the square root of both sides. You square both sides. You do something to both sides of the equation. In an identity, you don't cross the equal sign. You do stuff to one side, you can do stuff to the other side, but don't cross them. Okay? Now, There is no well-defined set of rules to follow in verifying trigonometric identities. So they say it's best to learn the process by practicing. Practicing. Okay? Yes. Pretty important. Here are some guidelines. They say there's no set of rules, but they give you guidelines rather than rules. Okay? Now, I'll read to you what they say, and then I'll tell you what I say. They say work with one side of the equation or the identity at a time. It is often better to work with the more complicated side first. There's nothing wrong with that. But you can work with both sides as long as you don't cross. You don't do any operations across it. You can simplify this side at the same time you're simplifying the other side. There's nothing wrong with it. They say with one at a time, well then you do this, and then you would do this. Why not do it both at the same time? You're doing the same thing as long as you don't cross. Look for opportunities to factor an expression. We've already been doing that. To add fractions. We've been doing that. To square a binomial. Okay? All right, be careful there, but square a binomial. Or create a monomial denominator. We did that. Okay? Look for opportunities to use the fundamental identities. Note which functions are in the final expression that you want. Sines and cosines pair up well. Secants and tangents pair up well. Cosecants and cotangents pair up well. Okay? Mostly because of your Pythagorean identities. Okay? But also your, in some sense, is your, let's leave the Pythagorean identity. So I would actually be a little more explicit than this. In fact, most of the time I am. If you've got squares on one side or the other, think in terms of Pythagorean identities. So if the preceding guidelines do not help, try converting all the items to terms to sines and cosines. You know what? I do that much earlier. If I don't see anything that's obvious, go to sines and cosines. And always try something. Even making an attempt that leads to a dead end can provide insight and say, hey, but what if I did this? Oh, yeah, that might work. So don't just sit there and say, I can't do it. Try something and make it work. All right. No new assignments there. We'll pick up at the next paragraph next time. Good deal. I gave everybody their second test, right? Second half of chapter 4. It's due, try to get it in within a week, but I want it before we get to the end of this chapter. Okay? So we got a fair ways to go. The sooner you get it to me, the sooner I can get it back to you. Hint, hint, for those people who haven't turned in the first test. There's 2 of them. Neither one of them were here today, though. I hope they'll be coming back. You can always see what you made.
Oh, I can see it.
Oh, yeah. It's out there on Blackboard, but also you can always look at it. You just can't take it home with you because I don't want you.
What I made right now?
Yeah, you want to see the score or the test?
It's
Just the score. Okay. Chelsea, 96. Very good. Very good. Oops, I was recording that. I hope you don't mind. I didn't mean to be recording it, but I was.